Okay, so please start.
Hello, everybody. Thank you for the opportunity to talk today. Today, I'm going to be talking about some recent work I've been doing with some collaborators at Lawrence Berkeley National Lab and at UC Berkeley on developing surrogate models for hydrodynamical simulations. So the goal of this work is essentially to map from a dark matter only simulation to a full hydrodynamical output. So things like gas temperature, gas velocity, and gas density. And the hope for doing that, to develop a surrogate model for this, is to avoid the extreme computational expenses of running full hydrodynamical simulations. The particular application we're looking at for this is twofold. One is to develop fast catalogs for next generation cosmological surveys, so things like DESI, surveys that will be looking to constrain cosmological parameters and fundamental physics using, say, Lyman alpha forest, which depends a lot on the hydrodynamical simulations, as well as performing forward modeling tasks. So trying to map from actual observed Lyman alpha forest signatures or other cosmological observables to the initial conditions, which requires having differentiable hydrodynamical simulations, which are currently very computationally infeasible unless we simulate it or unless we have a surrogate model for it through some deep learning method which will allow fast differentiation. So the particular hydrodynamical simulation we're working with in this case is the NIC simulation, which is compared to, say, like Illustris and the CAMEL simulations that people have been talking about throughout the course of the conference. NICS is somewhat simpler in that it doesn't involve things like active galactic nuclei or supernova or any of these feedback processes. So it's a little bit of a cleaner probe to work with from that standpoint. It's simpler, but it's really well optimized for studying the intergalactic medium, the more diffuse gas components, which is why we're focusing on the Lyman alpha forest here, because this is a cosmological probe that's very sensitive to the diffuse gas. And the key outputs for the NIC simulation, hopefully people can see my cursor. Oh yeah, I see that's moving there.
Yeah.
So the key outputs are the gas temperature, density, and velocities. And from those quantities, we can use analytical tools to map those to, say, the redshift space Lyman alpha flux, from which we can then extract Mach lines of sight and actually do the full analysis. So this particular kind of task of mapping from n-body to hydrodynamical outputs goes far before the development of machine learning techniques. People have developed various analytical approximations for this type of mapping from dark matter to, say, gas density. But with machine learning, we have a kind of obvious tool to use here. And from the machine learning community, from industry, there's a lot of great kind of tools that we could theoretically apply to map from these key dark matter quantities to the full hydrodynamical quantities. And by doing this mapping, in abstract save huge amounts of computer time. In general, for running a full hydrodynamical simulation, you're looking at a factor of maybe up to 100 times more time than just running the simple dark matter simulation. And from those hydrodynamical fields, we can then again map to the Lyman alpha forest flux. So people have probably seen, courses of conferences like this, or just even in, pop science news articles, the idea of image translation networks. So, you could do these crazy things where you take a picture of, say, a picture of Yosemite in the summer and then map it to the winter using image translation models. And so from these kinds of ideas, we're going to apply those tools that have been developed for mapping 2D fields to 2D fields to instead map three-dimensional fields, these hydrodynamical simulation, or these dark matter simulations, to another three-dimensional field, the hydrodynamical simulation. And today I'm going to be talking about two different approaches we've been working on in this manner. So the first one is an adversarial U-Net approach, which is going to be a deterministic approach, meaning that we give one dark matter field and we get out one hydrodynamical field. We don't have any stochasticity in this network. And then the second part, I'll be talking about a variational approach based on a variational autoencoder. And the idea here is that we'll actually be able to sample this posterior of all possible hydrodynamical fields that are consistent with the input dark matter field. And I am pretty excited about this approach because I feel like it has a lot of applications beyond just, say, Lyman alpha forest. But as we want to go to some more complicated hydrodynamical fields, if you want to start mapping not just to gas density, but to quantities like metallicity, AGN activity, star formation, these are a lot more stochastic of processes. And as we'll kind of show, a deterministic approach like the adversarial unit will actually wash out a lot of these kind of interesting stochastic features of our mapped quantities. So, So the first network here, kind of the most simple thing you could do almost is to apply a UNet structure. So this is kind of all the rage now in any kind of image based convolutional network. You have some input image. It goes through a series of convolutional layers and downsampling. Every time you downsample, you kind of save a copy of the output of the network before the downsampling and gets past these skip connections. So you downsample, convolve, downsample, convolve. Eventually you get down to a bottlenecked layer, which is kind of cut off by my Zoom screen thing. But yeah, so this bottlenecked layer here and then upsampled. And the idea of these UNet type architectures is you're getting a lot of multi-scale information from the network. And by using only fully convolutional layers, you're able to do cool things like train on subsamples of the volume. So in this case, we take a full hydrodynamical simulation, train these little subsamples, and then actually apply the same network fully consistently over a large volume. So in this case, what we did was we took a dark matter simulation, which had the same initial conditions as a full hydrodynamical simulation, just to match apples to apples. We took out subcrops of the full dark matter simulation, took advantage of symmetries and translations, and then compared the output of our UNet to the hydrodynamical simulation that matches with an L1 loss. This works decently well, but there are some kind of known failures of using an L1 loss. So here's kind of a classic image from machine learning literature, where I think in this case, they're using UNet to map from a labeled image, an image that shows the car, which pixels are cars, which pixels are trees, which pixels are streets, to the full actual real image. As you can see on the left here, all the small scale features kind of get washed out when you just use an L1 loss. L1 loss likes to push things towards the mean. Very sharp features are lost. And when we were training it without using any kind of additional loss terms, this is what we found for our Lyman alpha forest signatures or for our gas temperature and density signatures. But by adding in an L1 or by adding in a adversarial loss, by essentially training a separate network to try and distinguish between the generated image versus the true image and try to make it as confused as possible between those two, you can actually get much sharper results, as you see here in this right image. But when we try to now apply this to the case of full hydrodynamical simulations, you really have a huge amount of memory issues, because to train both these networks, generally speaking, adversarial networks need to be slightly more complex, have slightly more free parameters. And when you're taking in these, even though you're taking in subcrops of the image, it still is very huge in terms of the in terms of the memory constraints. So we had to do something to reduce the memory use. And so for that, we brought back the FFT. We ran off to Fourier space. Essentially, rather than operating on the real space images, we looked at their Fourier component and concatenated it significantly in Fourier space by essentially a factor of 8. And we found that this resulted in no real loss of image fidelity, but we were able to have a much more manageable sized input images to train on and significantly reduce the memory costs of the network. So put that all together, we're able to end up generating really accurate images of the Lyman alpha forest signatures. So here, for example, is the dark matter input, dark matter velocity, the true Lyman alpha forest flux. So this is essentially the, if you took one line of sight through here, that would be the absorption caused by the Lyman alpha forest. Darker means more stuff. lighter means less neutral hydrogen. And then you can see the predicted image down here. And on large scales, we agree quite well. You can look at the various statistics we'd be interested in for cosmological simulation, things like the power spectra or the probability density function. And in both these cases, we're able to really outperform the best analytical approximation. So here, FGPA is the kind of the best analytical approximation we currently have for this that doesn't involve running a neural network. And we can get extremely accurate results that are more than sufficient for, say, next generation cosmological surveys for things like DESI. But these types of models, despite doing very well in these kinds of summary statistics, still have some failures. So one kind of major failure of the model occurs when you have large rare events. I think we've kind of touched on this theme a lot throughout the conference so far, but large rare events are always difficult for neural networks to pick out. So for example, here is a very large shock.
Excuse me, 1 minute.
Where you had infalling gas and explosions of gas temperature. And these are really hard to pick out. And since I guess I'm running short on time, I'll just quite quickly summarize the solution to this, which is to introduce a latent space variable. And by constructing a network to essentially marginalize over this latent space variable, which we call the hyphy network, which is essentially a nested UNet structure, as well as a variational autoencoder structure, we can actually sample over this variational component and, given a dark matter field, generate lots of different realistic hydrodynamical fields. So I'll just show here, I guess, the main result of we have the gas dark matter, input dark matter density, input dark matter velocity, output gas temperature, velocity, and baryon density. And we're actually able to capture a lot of these shocks. And by sampling over this latent space, you can actually generate a lot of different realizations of these shocks. So here you can see in this upper left corner here, all these are just taking a different point in latent space, same dark matter field, and realistic shock examples. Meanwhile, areas which are hydrodynamically more boring, the bottom quarter here, are all very consistent throughout all possible samples. So it seems like by creating this variational autoencoder structure, this conditional variational autoencoder structure, we can actually really capture a lot of the uncertainty in these mappings, and we can then propagate those uncertainties to create things like variance maps, where is the model more or less certain of the hydrodynamical output, and then try to propagate those to, say, cosmological constraints. With that, I will, I guess, leave up my summary slide.
That's great. Thanks very much. So there's a comment from Mark on the Slack. He says, a nice way to add stochasticity in the units is the proba unit. See Hubert Bretonnier's talk on Monday.
I missed that talk, but I'll definitely make sure I look at the recording.
Hubert is in the audience, so can you pass it? You have a comment? Yeah. Could David Cornu come down to the...
Thank you for this great talk. Yeah, I had the question. I'm using this same kind of architecture, but more for segmentation, these unit things. And I had a specific question on that. You said that because it's fully convolutional, you can train on small images and then put bigger images and still have the same result. I tried that and it was not working that well. Did you see if you had if you lose some power on your simulation when you try bigger images or things like that? Can you comment on that?
Right. So I guess the main kind of concern, right, is if you have large spatial correlations that go beyond what your training volume would be. So it's nice for hydrodynamical simulations, for the most part, unless you're having something crazy like really huge astronomical shocks, your processes are fairly local. So in our case, for the mapping from dark matter density to gas temperature, say, unless you have these huge shocks, it's very local. And we found that this convolutional method worked quite well for the cases we were looking at. But I can imagine if you had larger scale features, it would no longer contain this kind of local property and might break down as you apply it to larger images.
Okay.
Okay.
Thanks.
We're going to have to move on to the next talk, so that was very interesting. Let's give Benjamin a round of applause again.